Hello everyone, and welcome to this video about cell-free massive MIMO with short packets. My name is Alejandro Lancho. I'm a Marie Curie Fellow at MIT, and this work was started during my time at Chalmers University of Technology. This is a joint work with Giuseppe Drisi from Chalmers University of Technology and Luca Sanguinetti from the University of Pisa. The main goal of this talk is to show how cell-free massive MIMO networks aim at providing support for ultra-reliable low-latency communications must be theoretically analyzed, as well as to explore, by means of numerical experiments, which are the advantages of deploying cell-free massive MIMO networks instead of cellular massive MIMO networks. It is well known that ultra-reliable low-latency communications require very small error probabilities and latencies smaller than 1 millisecond. The latter requirement implies in general the need of transmitting the information using short packets. Under such stringent latency constraints, exploiting time diversity is not possible, and exploiting frequency diversity is in many situations also not possible. Hence, the large amount of spatial diversity offered by massive MIMO arises as a very interesting solution to fulfill the requirements of ultra-reliable low-latency communications. Furthermore, the multi-user support of massive MIMO will also help to fulfill those stringent requirements. However, users at cell edges experience big path losses and large intercell interference, which may cause that the stringent reliability constraint cannot be satisfied when users are located at these positions. Cell-free deployments arise as a solution to this problem. The idea is to deploy access points with few antennas over the scenario instead of co-locating all the antennas in a massive MIMO base station. The access points are governed by CPUs that help with the coordination among access points. The advantage of these kind of deployments is that users are always surrounded by a number of access points, and therefore the cell boundaries disappear. Of course, at the expense of having to exchange more data with a CPU via front-haul links. An example of a cell-free network can be seen in the figure on the right. Cell-free networks has been shown to provide more uniform spectral efficiency over the coverage area than cellular networks. The question we want to answer in this talk is if we can expect the same advantages for ultra-reliable low-latency communications, and if so, how much we can improve with respect to the cellular deployments. Most works in the literature have focused on analyzing the spectral efficiency of massive MIMO. We have the works by Bjornsson, Sanguinetti, and collaborators, where they propose to use a TDD protocol where pilots are only sent in the uplink, and they use mismatched nearest neighbor decoding and treat interference and channel estimation errors as noise to then perform ergodic capacity analysis. Although their setup is suitable for the ultra-reliable low-latency communication setting, and in fact, we will use it too, the ergodic analysis is not. First, it requires coding over many coherence intervals. This is not possible if we want to convey the information within short packets. Furthermore, this analysis doesn't reveal the dependency of the results on the error probability. In the end, our goal is to characterize the achievable performance as a function of the packet length and the error probability. One alternative less explored in the literature to sidestep the aforementioned issues for this setting is the use of outage capacity. But is it outage capacity suitable for ultra-reliable low-latency communications? What is good is that the fading stays constant during the transmission of a code word, which is suitable when considering short packets. However, theoretically, perfect channel state information can be acquired for free. We simply need to send a sublinear amount of pilots, which is negligible as the block length tends to infinity. Furthermore, the attempts so far to address these issues rely on approximations whose theoretical validity is unclear. What justifies somehow the use of outage capacity as a performance metric at finite block length is the following. First, let's recall how the so-called normal approximation for Gaussian channels derived by Polyanskiy in 2010 looks like. The maximum coding rate is equal to capacity minus a penalty term that depends on the so-called channel dispersion V, and that vanishes as the block length grows, plus some error terms that also vanish as the block length grows. This approximation has been used recently by Nasir et al. In a not very convincing way to benchmark the performance of cell-free networks. In the quasi-static setting, Zhang et al. Showed in 2014 that the maximum coding rate converges to outage capacity much faster than the one corresponding to the Gaussian channel. In other words, the dispersion is zero. Now, the question is why this is not applicable to Massive MIMO. The point is that due to the large amount of spatial diversity offered by Massive MIMO, the so-called channel hardening effect appears, which makes the effective channel deterministic as the number of antennas grows. This implies that our effective channel will resemble an AWGN channel and outage capacity stops being a correct benchmark. In this talk, we propose a finite block length approach based on a rigorous non-asymptotic information theoretical bound, the random coding union bound with parameter S, which was introduced by Martinez and Guillén Fabregas in 2011. To derive our performance bound, we use Gaussian codebooks and mismatched nearest neighbor decoding. Due to the computational complexity of the bound, we propose an accurate but easy to compute alternative based on the saddle point approximation. It is important to highlight that our framework is general in the sense that it applies to spatially correlated channels, any linear combining precoding strategy, any pilot-based channel estimation method. It allows to study the impact of pilot contamination, and it is suitable for cellular and cell-free deployments. Our framework builds upon the following simple channel model, where the output, denoted by the vector V, corresponding to the transmission of the length n signal Q, is given by this simple formula. Here, G denotes the channel gain, and C is the vector containing the additive noise. The receiver does not know the channel gain G, but has an estimate G hat that is treated as perfect in the decoding process. We consider a mismatched scale nearest neighbor decoding, where the estimated signal Q hat is given by the code word belonging to the codebook that, once scaled by the channel estimate G hat, is the closest to the received signal V. This channel model is suitable for Massive MIMO. It simply requires mapping the transmitted signal to the vector Q. G would be the channel after combining or precoding, and C would be the vector that collects all the interference plus the noise. Let's see now how we obtain the finite block length upper bound on the error probability that we use as a performance metric. Our goal was to obtain an upper bound on the error probability epsilon achieved by scale nearest neighbor decoding. As usual in information theoretic achievability analysis, we used a random coding approach, and in this case, we considered IID complex Gaussian inputs. Rho here can be thought of as the transmit power. After some standard derivations, we obtain the random coding union bound. Here, M denotes the number of code words, which is related to the size of the transmitted messages. The problem of this bound is that it is horribly computationally complex. To relax this issue, we use the Chernoff bound over this probability term to obtain the RCUs bound, which is given here. Here, IS denotes the generalized information density. Still, this bound is computationally complex, especially when we aim at low error probabilities. The solution at this point is to perform refined asymptotic analysis over this bound. One option is to use the normal approximation of the RCUs bound, which is given by this Q function here. Here, IS denotes the generalized neutron information, and VS is the variance of the generalized information density. The problem of the normal approximation is that it is only accurate when the rate is close to IS, which is not always the case when we consider ultra-reliable low-latency communication requirements. Details can be found in our recent paper on ultra-reliable low-latency communications with Massive MIMO. The alternative to the normal approximation is the saddle point approximation. Although this approximation looks much more complicated, it is not. As we can see, for a given zeta, we need to compute the first derivative of the cumulant generating function of the generalized information density, which is known in closed form, and then we get a rate. Then we can compute the bound for this given rate, which depends on some functions that are available in closed form. Indeed, the saddle point approximation and the normal approximation, in this particular case, present the same computational complexity. IS and VS require evaluating two derivatives of the cumulant generating function of the generalized information density at 0, while in the saddle point approximation, we have one extra degree of freedom by evaluating the cumulant generating functions at different values of zeta. This makes the approximation accurate for any value of rate. Having said this, to obtain the final result, both approximations finally require averaging over G and G hat via Monte Carlo methods. Next, we will study the performance of a fully centralized, cell-free, multi-user massive MIMO network. With fully centralized, we refer to the case where the access points forward the incoming signals to a CPU for joint processing. We consider here a TDD approach where MP pilots are sent in a first phase so that the CPU performs channel estimation. Any channel estimation strategy is possible, but in our work, we have considered MMSE. Then it comes the uplink data transmission phase, where any linear combining can be used at the CPU. In this talk, we consider MR and MMSE. Finally, in the downlink data phase, the CPU uses the channel reciprocity to precode using the uplink channel estimates, via MR and MMSE precoding. The precoded signals are sent via front-haul links to the access points, which are in charge of sending wirelessly the data to the UEs. Finally, the UEs will rely on channel hardening to get channel estimates and to decode. We consider a simulation setup with a coverage area of 150 meters times 150 meters, 40 user equipments, MP equal to 40, so there is no pilot contamination, a block length equal to 300, and same uplink and downlink slots for data, a transmit power of 10 dBm, and 160 information bits. We consider a Rayleigh fading channel model that accounts for a spatial correlation and path loss, and a wraparound topology which provides some symmetry to this scenario. As a performance metric, we consider the network availability, which we define as the fraction of user placements for which the per link error probability, averaged over the small scale fading and the additive noise, is below 10 to the minus 5. Here, we have the network availability as a function of the total number of antennas in the system given by the product of number of access points L and the number of antennas per access point M, for both uplink in black and downlink in red. The upper figure is for MMSE combining precoding and the lower figure for MR. Solid lines denote cell-free with single antenna access points, dot lines cell-free with access points with 4 antennas each, and dashed lines stands for single cell network with co-located antennas at the base station. The first thing we can observe is that the cell-free setting with single antenna access points outperforms the cellular case. Also, the plot suggests that densifying the network is better than deploying less access points with a few collocated antennas in the downlink. This seems to contradict the results in the paper by Chen and Bjornsson in 2017, where they showed that channel hardening happens faster when the APs are provided with some antennas, although the network becomes less dense. This is also true in our case. However, our performance metric, which is the network availability, gets more benefits from densifying the network rather than improving channel hardening. Indeed, by densifying the network, the path loss is reduced, and hence, the average error probability also decreases. It turns out, these dominate the lack of channel hardening. Furthermore, we should use MMSE signal processing. As we can see in the lower figure, MR cannot achieve high network availabilities. With MMSE, the downlink is clearly worse than the uplink. This is because the channel estimation at the user equipment is performed relying on channel hardening. So the question is, what would happen to the downlink performance if we also use downlink pilots so the user equipments don't have to decode relying on channel hardening to obtain the channel estimates? In these simulation results, which are not included in the conference version of the paper, we explored the performance of using also downlink pilots so the users could obtain estimates of defective precoded channels. In this case, the setup is slightly modified. Now, the total number of channel uses available are divided in two parts, one for the uplink and one for the downlink. In the uplink, we transmit MP uplink pilots, and the rest is for data transmission. In the downlink, we will explore the case where all the slots are used for data transmission, and hence, the users rely on channel hardening to decode, and the case where MP downlink pilots are sent, and less slots are available for data transmission. We only compare, for simplicity, cell-free with single antenna access points, which is represented by solid lines, with a single cell network with collocated antennas, represented by dashed lines. In the upper figure, we have the uplink performance, and in the lower figure, we have the downlink performance. As expected, by the allocation of channel uses between uplink and downlink, the transmission of downlink pilots does not affect the uplink. This only impacts the available slots for downlink data transmission. We can see that when transmitting downlink pilots, the cell-free downlink performance gets close to the uplink performance. This happens because in a very dense network, using less channel uses to transmit data is not detrimental, since the path losses are very small and errors are unlikely. However, in the cellular case, transmitting downlink pilots is even detrimental in the downlink. Even though the users get better estimates of the precoded channel, decreasing the number of available channel uses for coding has a large impact over cell edge users, which decreases the average performance over the network. In other words, here it is more beneficial to decode relying on channel hardening and use stronger channel codes to protect the data against the communication impairments. Let's now wrap up and summarize what we have seen in this talk. First, we have presented a framework to analyze the performance of ultra-reliable low-latency communications with cell-free massive MIMO. It is based on the RCUs finite block length upper bound for mismatch decoding. We also proposed the saddle point approximation to evaluate the bound in an accurate and computationally efficient way. Our framework is general. It applies to spatially correlated channels, any linear combining precoding strategy, any pilot-based channel estimation method, allows to study the impact of pilot contamination, and can be used for cell-free and cellular massive MIMO networks. Finally, as a take-home message, we can say that for ultra-reliable low-latency communications, the performance of fully centralized cell-free networks is superior to the cellular one. Also, we should use MMSE signal processing. Finally, we've seen that the use of downlink pilots is beneficial but only in the cell-free case, where due to the access point density, the transmission of strong channel codes to combat the path loss and the channel impairments is not that important.